Hello everyone, today I will present the component-wise convergence theorem. Actually, this theorem is one of the most useful results when studying sequences in higher dimensions. It allows us to determine whether a vector sequence in Rn converges by checking each coordinate separately. Next, you can see the roadmap for today. And first, we will recall what convergence in Rn means. Then we'll look at the standard method that is usually used to check convergence. After that, we'll see why mathematicians wanted a simpler method, which leads to naturally to component-wise convergence theorem. And at last, we will of course, prove this theorem and finish with an application that shows why this theorem is useful in practice. Now let's begin with the definition. First, I want you to look at the interpretation part. In order to understand the convergence of sequences in Rn, we can simply refer to R and R square dimensions that we are familiar with very well. So suppose we have a sequence of points AK that's randomly actually located in both of our graphs. And suppose there is another point A. So we say that the sequence converges to A if eventually every point in the sequence becomes as close to A as we want. For example, if we consider the R dimension graph, we can see that after some value of large K, the points in the sequences are becoming very, very close to our points A in the middle. Yeah. And mathematically, this is expressed using the Euclidean norm in our definition. And we know that the norm measures the distance between 2 points. So when the distance between AK and A becomes smaller than any positive number epsilon, we say that the sequence converges. And intuitively, for example, convergence in R square, we can imagine as throwing darts closer and closer to the center of a target. And the center will represent the limit, and each dart will represent a vector or point in our sequence. Fortunately, there is another way to express exactly the same idea. Instead of using the epsilon definition directly, we simply compute the norm of the difference between given vectors. So if the norm approaches 0 as k goes to infinity, then the sequence converges to 0. And this criterion is mathematically equivalent to the previous definition, and it is usually much easier to apply when solving some practical problems. Now let's see how convergence is usually checked. Consider the sequence AK, which is 1 over k and 2 over k. Looking at the coordinates, we might already expect that the limits will be 0, 0. However, we still need to verify this using our Euclidean norm. First, we guess that our limits will be 0, 0, and then we calculate the distance from the sequence of points AK to the suspected limits. We subtract 0, 0, square each coordinate, add them together, and then take the square roots. And finally, we can get root 5 over k. As k becomes very large, this quantity approaches to 0, which means that the sequence converges to our guessed limits 0, 0. Actually, this method works perfectly well, but notice that it requires calculating the norm, simplifying the expression, and then taking the limits. So for more complicated vectors, if the sequence will have such one, these calculations can become even much longer and harder. Now let's observe something interesting. In the previous example, we discovered that 1 over k goes to 0, 2 over k goes to 0. And since both coordinates converge individually, the whole vector converges to 0, 0, and so our limit point A will be 0, 0. And here is the question. So do we really need to compute the Euclidean norm every time? Or is it enough to simply check whether each coordinate converges? So this question is exactly what the component-wise convergence theorem answers. And this theorem states that a sequence of vectors in Rn converges to A if and only if every coordinate converges to the corresponding coordinate of the limit. The notation pi simply means the projection onto the i's coordinate. And in other words, we can say that if every coordinate behaves correctly, then the entire vector behaves correctly as well. And the proof for this theorem has two directions because it's an if and only if statement. First, we prove that the vector converges, that the vector convergence implies coordinate convergence, and then we prove the opposite direction, showing that the coordinate convergence also implies vector convergence in Rn. And before proving either direction, we need to establish an important inequality to use in our proof. So notice that subtracting two projected coordinates is exactly the same as projecting the difference of the vectors. So this follows from the linearity of projection maps. Next, we compare the distance of one coordinate with the total Euclidean distance. And intuitively, we can imagine it as moving along one coordinate can never be larger than moving through the entire space. And therefore, we have this inequality. Actually, it becomes the key tool that allows us to connect coordinate distances with vector distances throughout the proof. Now suppose the vector sequence already converges. This means that the Euclidean distance between AK and A approaches to zero. From the inequality that we got on the previous slides, every coordinate distance is trapped between zero and its norm. Since the norm goes to zero, the coordinate distances must also go to zero, and this follows directly from the squeeze theorem. Therefore, we can state that every coordinate converges to its corresponding coordinate, following convergence criterion that we discussed in the beginning of our presentation. So vector convergence automatically implies a component-wise convergence. Now we prove the opposite backward direction. So assume that every coordinate converges. We now want to show that the entire vector converges. And instead of looking at each coordinate separately, we compare the Euclidean norm with the sum of the absolute coordinate differences. This inequality tells us that the whole distance cannot exceed the sum of the individual coordinate distances. And since every coordinate distance approaches zero, their finite sum also approaches zero. And therefore, the Euclidean norm is squeezed between zero and another quantity that also approaches zero. So again, the squeeze theorem tells us that norm must approach zero. Since the norm approaches zero, the vector converges, and together with the previous direction, we have proved both implications. And therefore, we can say and be confident that convergence in Rn and convergence of each coordinate are completely equivalent. And now let's apply this theorem to check how it works. We are given some sequence in R3. So instead of calculating a complicated Euclidean norm, let's first examine each coordinate separately. So first coordinate is 1 over k squared. Since the denominator grows without bounds, this expression approaches 0, and therefore the first coordinate converges to 0. The second coordinate is -1 in power of k over k. Here the sign, we know that it keeps alternating, and however, the absolute value is always at most 1 over k. Since both -1 over k and 1 over k approach 0, the squeeze theorem tells us that this coordinate also converges to 0. And the last coordinate is 1 plus 1 over k. Since 1 over k, we already know that it approaches to 0. The whole expression will approach to 1 because only 1 will be left. Since all three coordinates converge, the theorem immediately tells us that the vector converges to 0, 0, 1. And for comparison, out of our curiosity, we can check how we will find the convergence of it with Euclidean norm. So we put the Euclidean norm first and simplify it, and finally show that it approaches to zero after getting the answer of solving the distance expression, right? And when we got the zero, it means that our sequence converges to that suspected limit that we guessed. So it was 0, 0, 1. Since both methods give the same answer, we can be confident that the component-wise convergence theorem works. To summarize today's presentation, convergence in Rn is formally defined using the Euclidean norm, and however, the component-wise convergence theorem shows that checking every coordinate separately is completely equivalent. This transforms one complicated vector problem into several simple one-dimensional limits problems. So as a result, proving convergence becomes much faster, much easier, and more intuitive. That is why this theorem is widely used throughout multivariable analysis. And yeah, thank you very much for your attention.